Welcome everyone to the AAA Lecture. We're so glad that people could be here for our April 17th lecture. I was really bummed that we had to cancel or postpone our March lecture. So welcome everyone out on your couch, wherever you are tonight, hopefully safe and sound. Glad you could make it. My name's Irene Pease. I'm the president of the Amateur Astronomers Association. So usually we start these off as a little bit of a meeting, so I have some announcements and some updates from the club that I'd like to share, and then I'll be handing it off to our lecture coordinator to introduce our fantastic speaker for tonight. Bear with me, I'm a little bit new at this. So let me just pull up a slide. There we are. So the AAA lecture series, that's us, that's tonight. So again, I'll let our lecture coordinator introduce our speaker. But some of you might be wondering, what's happening with AAA these days? What's going on with that? So as of April 17th, that's today, the shutdown has been extended, so we have canceled our events, our public events through May 15th, so we won't be congregating before then, and we're gonna just kind of stay updated with what's happening, following recommendations of health and local government officials on that, as you all should as well. But we're still doing stuff, so it's not like astronomy doesn't happen anymore. One thing that hasn't changed at all is the eyepiece. So you can find that on our website. You're still getting updates for that. Those emails are still going out. And if you are doing anything exciting that you want to share with the rest of the club, please write an article, send it into editor@aaa.org. We'd love to hear what you're doing, astronomy related or otherwise. So eyepiece is still out there for you to read, to contribute to. We have 2 classes that are going to be running all online this spring. It's a new fun thing. Our last class that was taught by David Kiefer ended with the last 2 weeks online. So we're taking both classes for spring online. There's still openings in both of those. There's a Tuesday class that's going to be taught by Matthias Schmidt. That's starting this Tuesday, April 21st. And then the Wednesday class, planetary science class, will be taught by David Kiefer again. So that's a new class that he's developed. Really looking forward to that. Both should be really fantastic. And again, those are open to all of our members. We have these open to a few more than usual. And there are still spots available in both of those. So if you're interested, you can check those out on the website or in the members portal, aaa.org/classes. There's also links on the front page. So we have classes that are happening, very exciting. We also are going to be trying to do some kind of observing. We've already done, a couple of our intrepid observers and astrophotographers have done some ad hoc sessions. It's very weather dependent and equipment dependent. So kind of as soon as someone gets something set up, they might, press go live on the stream. So we're trying to keep on top of those and post those on our social media channels as soon as possible, but we might miss some. So if you want to try and catch some of the ad hoc live streams, make sure you're following us on Twitter, Instagram, and on Facebook. We do try to keep those updated. And then we might also have some scheduled visualizations. I'm going to be flying around using open space software, just kind of taking tours of the local universe. So some of those are on the calendar, but a lot of those will be ad hoc. So keep an eye out for those. We also have meetups that are still happening. Our astrophotography group is super active and they're still having their meetups on Sunday. So if you're interested, you can join that group. This is actually also my plug for the annual meeting. So a lot of you recognize the Zoom view. It's like we're all part of the Brady Bunch now, as someone was joking the other night. But our annual meeting, that's coming up May 20th. So that's still on the calendar. We're still doing that, but it'll be a big fun Zoom thing. And we're trying to figure out how to make that a chance for people to mingle, as well as just hear about all the updates of everything that's been happening over the last year, get updates from all the AAA officers. So please plan to be at that if you can. And as always, you can check our calendar for anything else that's coming up. The AAA calendar, a lot of stuff has been canceled, as you can see, but some of that might be rescheduled as an online event. So check our calendar, check the website, and stay safe out there, right? So without further ado, I am going to hand this over to David Kraft. He's our lectures coordinator. David Kraft is up at University Bridgeport. He's not there right now, but just wanted to give a shout out to his organization. So just one moment, I'm going to bring David front and center for us all so that he can introduce our speaker. David, you're on.
Whoops. Yeah.
So David, are you on there to go ahead and introduce our speaker?
There I am, yes.
Yeah. Okay, great.
I am ready to do that. I see myself on screen, and I guess I'm on audio, am I?
Yes, you're on.
Okay. Well, again, yes, I am. Indeed. Okay, good. So, again, there seems to be an echo. Irene?
You might want to mute the YouTube.
Okay. Yeah, I heard an echo, Irene, while you were speaking, or is there a delay? Is that due to the delay?
Yeah, there's a delay.
Okay, here we go. Okay. Again, let me then echo Irene's words of introduction and give thanks that we're all able to get together for we can't be in our usual setting at the museum. Our last 3 lectures had to be suspended. 2 of our lecturers, Priya Natarajan of Yale and Catherine Rhode of Indiana University, have agreed to present their lectures in person the next time that we're able to do so. Priya was to speak on the imaging of a black hole. If you remember last year when it was announced that a black hole had been imaged, it was she who wrote the op-ed article in the New York Times the day before the announcement. Catherine Rhode was to speak on globular clusters. Again, as I say, it's time that we are able to meet in person. Now, for those of you who don't know about these lectures, the series dates back to 20. And to my knowledge, there has never been any interruption. But we'll have to check that by looking in the archives and seeing if there possibly was an interruption during work. At any rate, we're ready to proceed then in the best way that we can, which is then this, our first live stream lecture. One of the lectures is designated as the John Marshall Memorial Lecture, and it is tonight's lecture that has so designated. Now, I must say at the outset that this is not the John Marshall who is the famous jurist, or the man that you studied when you studied American history. The John Marshall we're talking about is the former president of the Amateur Astronomers Association. In his many roles, he served as president and executive director. He was also a generous benefactor and is considered a key factor in the growth in the club's growth. John Marshall passed in 1997. So, without further ado, then, let me introduce this year's John Marshall lecturer. And he is Dr. Robert Coyne of the University of Rhode Island. Rob got a bachelor's and master's in physics at the University of Massachusetts, PhD in physics at George Washington University. Subsequently, he served as a postdoctoral research associate at Texas Tech University, and he joined University of Rhode Island, his present home, in 2017. Rob's research interests include gravitational wave astronomy, high-energy astrophysics, including gamma-ray bursts, and physics education research. He is a collaboration which, in 2016, announced the first direct observation of gravitational wave, and he continues in that collaboration. He has his many honors and awards are those which he has shared with that collaboration. In addition, Rob is active in activities. He makes many popular presentations of scientific topics, and he serves as mentor and advisor to high school students who are involved in research. Originally, when I met Rob a few years ago at an American Physical Society meeting when he gave a lecture on gamma ray bursts. And it was at that time I invited him to lecture in our series on that subject. However, we changed that because in this year's series was to talk on gamma ray bursts. And so I said to Rob, please select another topic and speak on gamma ray bursts at a later time. Tonight's topic is on gravitational waves, which of course is the subject of the work done by the LIGO collaboration. Rob has selected as his title, Crescendo of the Cosmic Symphony, Gravitational Waves and the New Frontier in Astronomy. So in any way that we can, let's give a warm welcome to Rob as he takes over and presents his lecture. Take it away, Rob.
Hello, everybody, and thank you all so much for coming to this talk. You know, we're living in really difficult times, so it's great that we can see so many people come together in the interest of learning about some really cool science, and that's hopefully what we're going to do tonight. You know, the topic of today's talk, gravitational waves. Hello, everybody, and thank you all so much for coming to this talk. Einstein himself, in his original papers, we're living in really difficult times, so it's great that we can see so many people that come together and someday be able to in the interest of learning about some really cool science, and that's hopefully what we're going to do tonight. You know, the topic of today's talk, gravitational. Hello, everybody, and thank you all so much for coming to this talk. Einstein himself, in his original papers, we're living in really difficult times, so it's great that we can see so many people that come together and someday be able to in the interest of learning about some doing so science, and that's hopefully what we're going to do. We are going to hopefully completely fix the audio issues that we're having. Okay. This is a brand new thing, folks. Sorry that it is all going haywire, but we're in this together. Just means that you're going to have a little bit of an issue here. Hold on. I'm so sorry, everybody. We're having some technical difficulties. Hopefully now that I've completely averted a potential catastrophe here in the form of loud sounds coming from my laptop, we'll be able to move on and tell something actually an interesting story here. So it wouldn't be a brand new type of lecture without a brand new type of problem. So with that aside, we are now going to go into what I was actually talking about, which is to say gravitational waves. Now this is something that has been around for the longest time. Einstein, in his original papers on general relativity, published interesting stuff about the idea that there could be ripples in the fabric of gravity itself. Took a long time before that became realized, though, in the form of astronomy that we're going to talk about today. Now, it took thousands of scientists, decades of hard work to get where we are, and I'm really excited to be able to share some of that with you now. Okay, with that said, let's talk about why you're all here. Space. Space is pretty awesome. It's full of all sorts of interesting things. Stars, asteroids, meteorites, clouds of gas called nebulae, giant explosions called supernova. And it's full of all sorts of amazing things that we've learned about over the past thousands of years as astronomers. Now, one of the things that we're going to want to be considerate of here is that although humans have been astronomers for a very long time, all of our observations and all of the amazing things we've learned about the universe have something in common. They came from light. You see, now, light is the thing that we use telescopes to look at. Now, sometimes it's the light that we can see. And famously, Galileo Galilei, 17th century astronomer, 17th century astronomer, used the spyglass, which had been around for a while, and he turned that spyglass towards the stars. Now, when he did so, he started to realize several really interesting things. Interesting things like the moon wasn't as perfect as everybody thought it was. It had dimples and spots and huge belts of dark sands and the lunar maria. He noticed that Jupiter had moons, something that had never been observed before, moons that orbited a planet that wasn't Earth. He even observed things like Venus and how it has phases just like the moon does. He catapulted our understanding of astronomy far into the future. But it was still an observational science back then. It wasn't until this man came along, Isaac Newton, and he gave us insight on the physical nature, the actual goings-on, what was happening at the basest level. He published entire ideas in the study of optics, the idea that light was actually consistent of individual colors, and that those colors could be represented as waves, and that these waves interacted with our eyeballs in a way that we could interpret in all sorts of different ways. And he was also, apparently, a Pink Floyd fan. Now, over time, we learned more about this wonderful electromagnetic spectrum. We realized that it stretched all the way from the radio, things like the Very Large Array, the things you see in the, Contact and other older science fiction films, all the way up through microwaves, the same thing you use to cook your food, and the infrared, up to the visible. That's where telescopes like Hubble live. Of course, Hubble's going to be going by the wayside here in the not too distant future, to hopefully be replaced by James Webb, which is going to operate in this part of the spectrum and tell us all sorts of amazing things about the universe. You keep going up to higher and higher energy, you get X-rays, the same thing the dentist takes pictures of your teeth with, up to the gamma rays. And this is where I live. I work mostly with observations made by these satellites right here, Fermi and Swift. Now, because we've had such a long time to make observations across this entire spectrum, we've been able to see some pretty amazing things. But like I said, all of these observations have something in common, and that is they're made with light. You can always turn the lights out. To illustrate why this is worth mentioning, I'm going to play you an important scene from a film that you might recognize. Of course, I don't have the audio to play for you, but that's fine. I wasn't going to play the audio anyway, because I'm using this to illustrate a point. Here's a scene from the famous film Empire Strikes Back, and don't worry, no spoilers. Here we see the protagonist of the film face to face with the antagonist of the film, and they're having a discussion at the film's climax. Now, we don't have the sound on, so we can't hear what we're saying. We can read the protagonist's lips, that's fine. But the other one's protected by a mask. Can't read his lips. Don't know what he said. Whatever it was, seems like it was kind of a big deal. And that is the key issue with light. You can always put something in the way. You can block it out. And I mean, we're all blocking out the light right now. There's a sun out there. There's a roof over our head, that's blocking it out. You can just hold up the hand and the light from the screen, it's not going to reach you anymore. You won't be able to see me and all of my wonderful technical difficulties. This is because light is easily blocked. So there's a lot of stuff happening out there in the universe that we can't necessarily see. And so we turn to gravity for an answer here, to look into the places where we can't actually see with our eyes. And to understand gravity, we have to go back to Isaac Newton. Now, the story goes that Isaac Newton was sitting on in his garden and he saw an apple fall from a tree. Spoiler alert, that is not what happened. But he was famously perplexed by how the same force that pulls an apple down to the ground also keeps things like the moon in orbit around the sun. Oh, sorry, moon around the sun. Moon around the Earth, and the Earth around the sun. And so he set his mind to coming up with a theory that connected these things. And his theory of gravity was beautiful. Now, don't mind the math too much. Newton's theory of gravity is pretty straightforward. He says that anytime there are two objects that have mass, they feel an attractive force. They're pulled together. Now, if you make those masses bigger, the force gets bigger. If you put those objects further away, the force gets smaller. And you can use Newton's theory of gravity to do all sorts of great things, including explaining orbits, for example. We sent men to the moon using Newtonian gravity. But while Newton's theory does a pretty good job, especially for being 400 years old, at explaining how gravity behaves, doesn't quite tell us where it comes from. For that, we have to turn to another smart gentleman. This guy right here, you might know him, Albert Einstein. Most notably, most known in the popular media for this equation right here, E equals mc squared. The equation that TV producers write up on the whiteboard whenever they want to make sure the audience knows a character is smart. And that's because Einstein was a pretty smart guy, not gonna lie. And he was really interested in how different people observe events. His famous theory of relativity relates the physical measurements that different observers will make of the same event. Consider a simple example, a couple of cars driving down the highway. Now, if they're driving towards each other, they're both moving, but if I'm sitting in the car over here, I see that car moving towards me. By contrast, if I'm in this car, I see the other car moving towards me. Both of these people see slightly different things, and in some cases that leads to physics breaking down just a teeny little bit. And that bothered Einstein. See, he felt that the underlying physics, the actual reality that's going on there at the most fundamental level, really shouldn't depend on how you're looking at it. And so he redefined our understanding of both space and time, and in doing so discovered a new and beautiful truth about gravity. Now, interestingly enough, to do that, he started with a ruler. Because we have to talk about how we make measurements. That's at the core of Einstein's relativity. And we start by just defining a unit. If I'm a scientist, this unit's probably a meter. If you're here in America, maybe it's an inch, a foot, or if you're a football fan, maybe it's a yard. You can turn that unit into a ruler by putting a whole bunch of them in a row. That allows you to measure length. From there, you can add another ruler to measure width. And from width, you can go up a third axis and get height. So this is just a three-dimensional coordinate system, a way that we measure things in 3 whole dimensions. But that's not the only measurement we can make. Einstein realized that time, how much time has elapsed. For example, here we've been in this meeting for a nice 24 minutes. That requires we have a clock. Now, consider that clock down there. Probably tells really good time, but if I am all the way up here, I probably can't read it. It's pretty far away. So instead, we take our three-dimensional grid and we put a clock at every grid point. We work really hard to make sure all of those clocks are synchronized, and now, no matter where I am in space or time, I can always make a measurement. Now, this whole thing here, this measurement system, is the concept of space-time, the thing you've probably heard about in movies. And really, it's just how we measure things. Just these simple things that we measure in our day-to-day lives. Now, of course, this diagram here is pretty complicated. Whew, I'd hate to have to carry this around all night, right? So let's go ahead and smooth that down a little bit and just represent it with a nice flat plane. We're pretending that the big, complicated mess on the left actually can be represented by the thing on the right. And that's the framework for where we're going from here. Now, Einstein spent a lot of work figuring out the mathematics of these measurement systems. And my general relativity students who are in this lecture will recognize the Einstein field equations up there. And if that looks intimidating, they just ask my students. They can tell you it is. But we're going to break it down into something digestible. That first bit that I just blocked over, that's just a number. It's a thing that scales to make sure all of our measurements come out right. The thing to its right, that t, that's just a mathematical tool that we use to describe matter and energy, where matter is and how it's moving around. And that whole mess of stuff on the left, that's a formula that describes the curvature of space-time, the way that that measurement system we just talked about bends and twists. In doing so, we can now relate the curvature of space-time to the presence of matter. So, if you have no matter, you have flat space-time. But if you have dense matter, space-time itself, the very measurement system we use, bends around it. You can also read this equation the other way. Matter might tell space-time how to curve, but curvature of space-time in turn tells matter how to move. If I roll a ball right across a flat table there, it just moves in a straight line. But if I try to roll that same ball across a curved space-time, we're going to see that its path deflects, it bends. It looks like the motion is curved. And that right there is gravity. The effect of that curvature, bending the path of objects, is how gravity manifests itself. So the Earth is actually trying to move in a straight line, but the sun distorts gravity so much, the fabric of space-time so much, that the actual motion of Earth looks elliptical. And you can imagine if I can bend space-time in big, smooth ways like this, I should also be able to make ripples in space-time. And those ripples are exactly the gravitational waves that we're talking about today. And so for the rest of this talk, we're going to be talking about how we search for these ripples in space and time, these tiny, minute fluctuations in the strength of gravity. Now, this is a story that is 100 years old. Einstein first published his papers in 1915 and 1916 describing this. But it took a while for gravitational waves to really land and actually become a real thing that we could possibly do science with. And the first real observational discovery that said that maybe this was a good pursuit was the Hulse-Taylor binary system. Now, Hulse and Taylor were astronomers who were looking up at the night sky, and they saw a peculiar set of stars, really dense things called neutron stars, we'll talk a little bit more about them later, that were orbiting each other very, very close. Now, if you believe general relativity, you know that anytime you have a couple of things orbiting each other like this, they're giving off gravitational waves. When you give off gravitational waves, that means your system loses a little bit of energy. And in orbits, that means your system gets a little closer together. Each time you go around, you lose a little more energy, get a little bit closer, and a little bit closer. And Hulse and Taylor took this star system and used general relativity to predict that their orbit would get a teeny bit smaller every year. Smaller orbit means faster motion. Faster motion means it takes less time to complete one orbit. In over 3 decades, they compiled data from 1975 up through the 90s, and we even continued it on to the 2000s. And they took those red data points, those are the ones that they measured, and you compare that to the blue line. the prediction made by general relativity, which comes from the emission of gravitational waves. This agreement was so spot on that Hulse and Taylor were awarded the 1993 Nobel Prize in Physics, and this discovery was widely considered to be the first unequivocal proof that gravitational waves were real. But we're still a long way off from being able to do anything with them. Because to do that, we would need to build a telescope for gravitational waves. But how do we build a telescope for gravity? Well, one way is with bowling balls. Okay, bear with me here for a second. What you're looking at is an arrangement of masses, say bowling balls, and I've just put them in a circle on the floor. And what I'm going to do is I'm going to send a gravitational wave straight through the center of this arrangement of bowling balls and watch what might happen. The arrangement of masses will feel alternating stretches and squishes in different directions. That's the effect of gravity, spreading them out and pulling them back together as the ripple passes through them. Now, the strength of the gravitational wave governs how much stretching and squishing happens. And we can quantify that by comparing the maximum size, or the regular size rather, to how much the size of that arrangement changes. We measure that with something called strain, and for those of you who've seen scientific notation, you know that that is a tiny number. If you have no idea how tiny that number is, don't worry about it. It's fine. That number is so small, we really can't wrap our heads around it, even those of us who do this for a living. Suffice to say that strain measures the strength of gravitational waves, and it is a really small effect. Of course, bowling balls seemed like a super complicated way of building a detector. Wouldn't it be easier to, like, I don't know, just get a couple of rulers and watch how those rulers stretch and squish? That seems like it's easier. Well, if this seems like it's a kind of simplistic toy model, like how could you actually build a telescope like this? I've got news for you. It's exactly what we did. Now, we didn't use regular rulers. Regular rulers are too boring. We used lasers, because everything is better with lasers. This is the Laser Interferometer Gravitational Wave Observatory, which is a huge mouthful, so we just call it LIGO. I'm a member of the LIGO Scientific Collaboration, this folk right down here. And this is one of the several gravitational wave detectors we have in the world. There are 2 LIGO detectors currently, one in Washington State and one in Louisiana. And we also have partners all over the world, Virgo in Italy, GEO, and we recently, CAGRA in Japan. Now, we use lasers to measure very minute changes in length caused by gravitational waves. And I'd like to show you a video for how that works. So this is a really simplified version of our setup, and basically we're going to shine a laser, and we're going to split it in half, and we're going to watch how that laser interacts with itself. First, I'll let it just play for you. Gravitational waves will move the mirrors at either end of this setup, causing the light to fluctuate. Let's take a closer look. Light goes into an object called a beam splitter, which splits it perfectly in half. The light travels down the detector, bounces off a mirror at the far side, and then travels back to the beam splitter, where it recombines with its wayward partner, such that when everything's normal, they cancel each other out exactly. Now, when a gravitational wave comes through, it moves the mirrors just a little bit, just like it moved the bowling balls. That causes the laser light to fade in and out of sync with each other, which manifests as flashes of light that we can measure. We can very closely measure what those flashes of light look like and figure out the nature of the gravitational wave that went through our detector. Now, let me pause for a second here to give you a sense of scale. Now, gravitational waves, we already said, have a strain of 10 to the minus 21 meters. Each arm of LIGO is 4 kilometers long. That's 4,000 meters, or roughly 10 to the 3 meters. If you multiply these two numbers together, you get 10 to the minus 18, kind of on average. Now, this is a really small number. In fact, much smaller than I am now. Let's try to get a sense of just how small that is. Now, we already said the LIGO arms were something like a kilometer long, 4 kilometers, but we'll just call it 1. I'm an astronomer. What's an order of magnitude between friends? Now, if you take that, a kilometer, and you divide it by 10, you get something about the height of the Statue of Liberty, something you New Yorkers will know something about. You take the Statue of Liberty, you divide its height by about 100, and you get the normal height of a human individual like you and me. Something on the order of a couple of meters. You take a human height, you divide it by 10,000, you get the width of a human hair. So you can see we're already getting pretty small. Divide that by 100, you get the size of a yeast cell. Divide that by 10,000, and we're finally down to the size of an atom. 10 to the minus 10, also known as an angstrom. We're still really far away though, folks. You got to divide the size of an atom by 100,000 to get the size of the nucleus of that atom. And you got to divide that number by 1,000 to get down to where we're at for the change in length of LIGO's arms. Want an idea of how small that is? Well, imagine this is an atom. Nucleus in blue with an electron spinning around in a quantum mechanical cloud out there in red. Now we're going to take this atom, which starts off at about 10 to the minus 10, and we're going to zoom on in until we get down to the size that LIGO's talking about. When we get to 10 to the minus 15, we fly by the nucleus, and we keep zooming in on its edge until we get here. That is how much the length of LIGO's arms fluctuates, and we have to measure it. Thus, in order to be detectable, it's pretty important that gravitational waves be from really massive objects that are moving really quickly. What kind of objects, you ask? Precisely the sort that you came to hear about. Black holes are a great example. Black holes are stellar objects so massive and so dense that not even light can escape their gravitational pull. Now, before we go any further, I want to mention that there are two kinds of black holes. The supermassive kind, those are the ones in the center of galaxies, and the stellar mass ones, the ones that are a few times the mass of our sun, maybe a few tens of times, or maybe even 100 times the mass of our sun. Those stellar mass ones are the ones we're talking about today. To get an idea for the scale of this, let's put it in terms I think we can understand. The Earth, right? Pretty sweet Earth. We're familiar with this. Earth is pretty big, but it is tiny when you compare it to, say, the sun. Now, let's zoom out a bit more, make the sun so, we're pretty far away, and so the sun is going to be about this big now. We're pretty zoomed out pretty far. And let's add, I don't know, something like 29 other suns. So we're up to around 30 times the mass of our sun now. We're going to squish all those down into one gigantic star. And now we're going to take that gigantic star and we're going to squish it down so far that it could fit in the state of Missouri. This black thing right here is the size of a 30 solar mass black hole. And what we're going to do is we're going to take two of them and crash them into each other. What you're looking at here is a computer simulation of two large black holes spiraling around each other, just like the Hulson-Taylor binary. Now they're very near the end of their cosmic dance. They're going to get so close that the distortions in gravity get so strong that space-time gets bundled up and twisted up until finally the point where those two black holes merge into a single, much larger, black hole. As we zoom out, we see that the violence of that effect was so strong that it created ripples in the fabric of space-time itself, and those are the gravitational waves that we are discussing. Now, this down here on the bottom shows a theoretical plot of what the gravitational wave function might look like. But I'm going to zoom in a little bit and show you here. These are analytical predictions for what that should look like if it were to appear in our detector. And on September 14th, 2015, that is what we got. I mean, I don't know about you, but even just a casual glance between this stuff here on the right and this stuff here on the left probably convinces you that these two things are the same. And so this was really the universe's way of, thanking us for our patience. It took 100 years to get where we were, thousands of scientists, so the universe decided to make our first ever detection a big one. And boy, oh boy, was it actually big. I'm not going to show you this slide because it depends on audio, and instead we're just going to jump straight over to here. Not this one either. The binary black holes that crashed into each other were huge. Each one of them individually was about 30 times the mass of our sun. One of them was slightly larger, 36 times the mass of our sun, compared to 29 for the smaller one. Now I want to mention each of those individually. So these two things here shown in the diagram were each individually more massive than all of the other stellar mass black holes that had ever been discovered using more traditional astronomy. And they merged together to form a black hole even larger, 62 solar masses. Now, wait a minute, hold on. I hear what you're saying. Even if you're not a physicist, you can do arithmetic. And you might note that 36 plus 29 does not give you 62. That's because 3 whole suns worth of mass was converted into energy during this process. Remember Einstein's equation, E equals mc squared? 3 times the mass of our sun got turned into energy radiated away from gravitational waves. That is huge. This was such a monumental discovery, first ever direct detection of gravitational waves, first ever binary black hole merger detected with confidence, largest black holes, you name it. This was such a momentous discovery, it was awarded the 2017 Nobel Prize in Physics to these 3 luminary gentlemen, Ray Weiss, Barry Barish, and Kip Thorne. So that's Nobel number 2 for the gravitational waves. But if you ask my mother, the probably bigger accomplishment was that it also made it onto Sheldon's t-shirts in The Big Bang Theory. Now, this first detection opened a brand new era in astronomy because for the first time we were able to use gravity to tell us stuff about what was going on out in space. And so we started listening to the universe with gravitational waves. Because I want to emphasize, this gravitational waves, not quite like sound, but definitely not light either. So it's like we have a new sense. Now, I want to mention that after that first discovery, LIGO kept observing. And over its first observing run, which was only 3 months, it detected 5 more events for a total of 6. None of them were quite as massive as that first merger, but there were several other interesting events in those first few months. Sorry, there were 3 in the first observing run. And then, after that, we got some more. Now, this plot, super outdated. It's like 3 years old. Because a year later, in November of 2018, LIGO announced even more detections. And towards the end of this, Virgo had joined us in the pursuit as well. GEO worked alongside us the whole time. Now, these 4 new detections brought the total up to 10, but that information's outdated too, because in August of 2017, specifically August 17th, 2017, we saw this in our detector. Now I'm going to show you some data. The bottom plot over here, so that's down here. This is going to be from LIGO. And what you're going to see is a little zoop, a little line of light that skirts up. That's the telltale sign of a merger event. And up here, you're going to see gamma rays from the Fermi telescope. So here you see our gravitational wave signature, a nice bright line going. There's our merger. And just a couple of seconds later, we see this little flash right here. See, this flash was something called a gamma ray burst. And it occurs when, this is not the only way gamma ray bursts can occur, but this particular event occurred when we take 2 neutron stars, the same types of things that Hulse and Taylor discovered, and instead of just seeing them orbit each other, we see them crash into each other. Now, to give you an idea what a neutron star is, imagine we went back to the sun, we squished it down to a size that could fit in Boston Harbor. Go Red Sox! I'm not ashamed. This thing right here is not quite as massive as a black hole, but it's definitely very dense. And if you take 2 of them and smash them into each other, it might look something like this. Here we see 2 neutron stars in a cosmic dance, an artist's rendering anyway. They decaying from gravitational waves until they finally get so close that they actually merge together and touch and release a huge amount of energy in a violent explosion called a gamma ray burst. That gamma ray burst, which was the highly collimated flash that went off at an angle here, are really high intensity gamma rays. that event is followed up by something called a kilonova, which is basically like a mini supernova. Now, this was really super interesting because the first time we've seen gamma rays for 40 years, since the Vela satellites were observing the nuclear test ban treaty in the Cold War, and we had always long suspected that they came from binary neutron star mergers, but we didn't have the proof. This event was that proof. And it led us into a whole new era of multi-messenger astronomy that let us learn so many interesting things about what happened. Here's how that happened. We had dozens of observatories all over the world. LIGO and Virgo, shown in yellow, those are the gravitational wave detectors. But we also had something like 70 observatories all across the electromagnetic spectrum, from gamma rays and X-rays in space to optical and radio telescopes here on the ground. They all looked at this event and they all mined for information. And let me show you the timeline of what we learned. Now, right away, with the gravitational wave detection, that was the first thing that we saw, we already learned interesting stuff. What are neutron stars made out of? We could even use it to measure the rate at which the universe was expanding, and good news, we're in agreement with other measurements. Now, 2 seconds later, the gamma rays were detected from the gamma ray burst that I mentioned. Now, this allowed us to do some things that we weren't really able to do before. One of them was we were able to pin down, finally, the cause of some gamma ray bursts, have that real proof that some of them come from binary neutron star mergers, but because these are carried by gravity and these are carried by light, we were able to compare the speed of light to the speed of gravity. And they are the same, much as we suspected using our best modern understanding of physics. Now, after the gamma ray burst is when all of the other observatories kicked in. Within the day, optical and infrared light were detected, all the way up to ultraviolet light. X-ray light continued to be detected for over a week afterwards, and these allowed us to observe the kilonova. And the kilonova is what allowed us to observe the fact that there were a ton of heavy elements created in this explosion, things like gold and platinum. Now, this is interesting because it actually turns out that in a regular stellar furnace, like in our sun, you can't get materials heavier than iron. So it's long been a mystery how exactly all of the heavy elements that make up the other half of the periodic table came to be into existence. A lot of it comes from supernova, but we couldn't quite pin down the exact ratios. This event allowed us to conclude the way these heavy elements were created and how they ended up here on Earth. Observations of this will continue for months after in the radio and beyond, and we continued to learn more about this event. Now, I want to mention that all of this really awesome stuff that you see here, well, the only way we were able to learn it was because we saw both gravity and light. If we just saw gravity, that's all we'd get. If we just saw light, that's all we get. And we would have had to have been lucky enough to see this event in the first place. Not likely, because although this was a very energetic explosion, it was also really far away. And so it was very dim and hard to see. Only with all of this stuff together were we able to learn as much as we did. And so we have to update that plot I was showing you earlier, where before we had all of these black holes, to now include also this pair of neutron stars. Whew, great, we made it. Except this is outdated too. And the reason this is outdated is because just last year in April, LIGO and Virgo turned back on again for their third observing run. And, well, to say it was a productive exercise is a little bit of an understatement. The first month it was on, we saw another 5 events. Second month, what was that, 2, 4, 8 more? 6 more? 12 more? I don't know, I can't count, I'm an astronomer. Don't take that seriously, folks. Astronomers can count, just not me. After that, we kept seeing more and more and more events, and some of the things that were happening here were really super interesting. Now, the one, this one on the 10th, that's actually not a LIGO thing, but I do want to mention it because, yeah, pretty big deal. first ever image of an actual black hole. This is one of the supermassive kinds, so not the same ones that we study, but the Event Horizon Telescope did a really amazing thing in producing the first ever really true image of a black hole at the center of a galaxy. We also detected another binary neutron star merger. That's a second one there. And then after that, we started to see new and interesting things that we hadn't seen before. We're still studying a lot of these new events to really pin down what they are and if they really represent new science or not. And all of this stuff, I want to mention, happened before the 4th anniversary of the original detection. Just 4 years, folks, and we went from having never barely even dreamed of being able to do this to being able to do it regularly every single month at a rate of roughly once a week on average. Whew. Awesome, right? Except that's outdated too, because that was only the first half of 03. After that, LIGO and Virgo shut down for a month to recalibrate their systems, and we turned it back on. And that had actually been going all the way up to March of last month. But like everybody who's being responsible during this global pandemic, LIGO and Virgo decided it was in the best interest of their communities and their scientists to suspend the rest of 03 and just make sure everyone was home, happy, healthy, and safe, just like I hope all of you are. But we still saw a lot of interesting things in that second half of 03. And you'll notice that starting from our first observing run, where we only saw a couple, and our second observing run, that's when we got up to around 10. So 3 in 01, 8 in 02. It was 03 that really started to let things take off. We now have a total of 67 confirmed events, many of which have been put out into the wilderness in the form of public data releases. Now, this is a team effort. I am a member of the LIGO Scientific Collaboration, but I am by no means the only person studying this. We have a collaboration of over 1,000 people, and they aren't all in LIGO. So I want to take a moment to give a shout out to our gravitational wave observing partners. Now, LIGO Hanford and LIGO Livingston, that's LIGO, that's where I work. LIGO India is a planned installation that's going to go into operation sometime in the 2020s with any luck. Not 2020s, sorry, like sometime between now and 2030. Geo and Virgo are our European counterparts, and Kagra, listed here as under construction, is a Japanese observatory that, well, will hopefully join us soon. Except, I keep forgetting, this is outdated too. Because Kagra actually turned on and began observing February 25th, 2020. That's just this past year. Now, I hope over the course of the last 40 minutes, I have convinced you that we are in a brand new age of astronomy. Because we don't have just the one sense anymore. We have a whole new one. And unfortunately, I've stopped a little early because the sound on my laptop didn't quite play. But there was a running shtick that this actually could be somewhat similar to the sounds that we might hear. The reason for that is because if you take the data coming from LIGO and Virgo, and soon Kagra, and if you take that data and you put it into a computer program that converts the data into sound, you could actually play it back like an MP3. And the gravitational wave frequencies correspond to the frequencies that the human ear hears at. So if we were able to have ears sensitive to gravitational waves, it might be like we were listening to them. Of course, we don't. I don't know about you, but my ear cannot detect sounds down to 10,000 times smaller than the radius of nucleus. My ears are just not quite that good. And so as a result, we often do use sound as an analogy. But it's not quite necessarily the case. So I want you to be careful. Another way to think about it, that's maybe a little bit more inclusive, is that if the universe is a movie, this is what we see on the screen, and this is the soundtrack, or we could always be reading the closed captions. Now, I'm really sad, unfortunately, that this last little shtick I can't share with you because the laptop audio wasn't quite working. But it was finally a resolution to the big question of what our nefarious antagonist of the Star Wars film was up to, what he was talking about with our protagonist, Luke. Suffice to say, in this little clip here from Robot Chicken, he's telling him all about the midi-chlorians. And, well, Luke says, look, man, if you're not going to take this seriously, I'm out. And with that, I'm out. So sorry that we ran a little bit under time. I would have liked to have spent a little bit more time talking about all those great videos with the audio, but we just didn't quite have the technology down. So what's going to have to happen next time is you're going to have to come see me in New York sometimes next year, fingers crossed, if everything goes well with the COVID-19, for the next one of these lectures. Or, you can get involved with us in the meantime. So, for example, if you're interested in gravitational waves, well, we're not taking data right now, but we will be again later. And you can keep track of gravitational wave events by going to the App Store on your relevant device and downloading the Chirp app, which gives you notifications whenever there's a new event. If you'd like to contribute to the science, but you're not necessarily a scientist yourself, or hey, maybe even if you are, we have this cool project called Gravity Spy, where we use real LIGO data, let you, folks out there in cyberspace, take a look at it and classify the crazy noise that we see in our detectors. We use that to train machine learning algorithms to better identify the noise sources. And you can do this even when we're not taking data. That's a way you can actually get involved in the science itself. And of course, you can follow us on social media. That's me right there. I'm on Twitter mostly, and maybe a little bit of Instagram, and the relevant PR handles for our various other institutions. So thank you very much for coming to this lecture. I hope that you learned something, and I again apologize for being a little bit short and fraught with technical difficulties at the beginning. If you're interested, give us a follow. We'll keep you in the loop when more interesting things are happening. And at this point, I would love to take a look at some of your questions. So I'm going to go back and I'm going to comb through the chat, so stick with us. If you want to ask questions, just throw it on into the chat there. I'm happy to answer anything that you could possibly ask me about this. And stick around. There's going to be some more interesting stuff here, but I'm just going to take a moment to keep up with the chat. All right, we're back. I'm caught up. I'm going to get some of the easy questions out of the way first. One of my favorite that I don't think you'll be expecting a actual answer for, but I'm going to turn it into one. One of those questions was, sure, LIGO can see gravitational waves, but can it see why kids love Cinnamon Toast Crunch? And the answer is actually probably yeah. The reason being is LIGO and Virgo and other interferometers like that are super sensitive devices. We have to construct extremely high precision optical equipment that's sensitive to all sorts of things. Heat from the laser, vibrations due to earthquakes, or even just as simple as vibrations of somebody walking around or a cell phone going off. In fact, our detectors are sensitive enough to pick up when a truck drives by and goes over the rumble strips on the highway, or even when an alligator is deciding to shed its scales off by rubbing against the concrete enclosures of our beam arms. Now, because of that, if you got a kid in one of the LIGO detectors and you gave them a bowl of Cinnamon Toast Crunch and they started eating it, I bet that could show up in our detector if you weren't careful. So the answer is probably yes, LIGO can. There was another question right around there that asked about light fluctuating on the subatomic level. This was when we were talking about the beams going back and forth and the big arms. The answer is that the drawing that I showed you is, of course, a little bit simplified for the nature of a talk like this. We actually have some really high precision equipment inside the beam tube that sets up what's called a resonant cavity. So laser light comes into the beam arm, and yeah, it goes down the end and bounces off the mirror. But then there's another mirror here that traps it, keeps it from getting out for a little while. It bounces back and forth, 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 many times, which effectively makes the arm seem like it's longer. So we're actually able to detect very small vibrations because it adds up over all of those trips back and forth. So this isn't quite quantum gravity level yet. In fact, quantum gravity is a wonderful, interesting idea that we don't have an answer for yet. So if there are any kids out there in the audience right now who wants to, grow up to become a scientist, there are open questions, and that's one of them. Okay, now catching back up, let's see what else we have for questions here. The next question that I see is, how long ago did said events occur that we're just now sensing? The answer is quite a long time. These events are right in our backyard, cosmologically speaking, because the universe is very big, but in terms of day-to-day distances, they're actually quite far. Usually on the order of something like 1 billion light years or something like that, which is a long way for the gravitational waves to travel. In fact, since they travel at the same speed light does, many of these merger events actually happened billions of years ago, and their signals are just getting to us now. Some of them are closer, so maybe 500 million. Some of them are really close, a few tens or hundreds of million. Some of them are even further away, multiple billions of light years. Suffice to say, they're pretty far away. The next question, which is an excellent one, is if gravitational waves have the same speed as light, why did we see a 2-second lag in that signal? This is going back to the gravitational wave that we saw from the binary neutron star merger here. Why was there 2 seconds? And the answer to that is because different emission mechanisms. This stuff comes from the actual process of the bodies orbiting each other. So it's the spiraling together and the merger that produce the gravitational waves. But then the two neutron stars hit each other and they have to explode. And that explosion takes a little bit of time. They're not instantaneous. And so there is a slight lag before the explosion starts emitting light. And that's why we see the 2-second time delay. The next question that I see is a two-parter. Does seismic activity disrupt LIGO observations? And related to that, how do we know that the vibrations that we're seeing are from gravitational waves? And the answer is yeah, absolutely. LIGO is super sensitive to seismic activity. Now we have really complicated suspensions on our mirrors that really damp out those vibrations. So if you're walking down the hall, don't worry, you're not going to break anything. But if you have a giant earthquake, even one on the other side of the world, that will show up as little spikes in our detector. Now, we actually have a huge system of sensors tied into all of these things. Multiple channels of data measuring everything from the temperature of the mirrors to the amount of seismic activity going on to the ambient temperature in the beam cavity, probably to how much time is left on somebody's microwave trying to make lunch in the control room. All of those things give us slightly different measurements about what's happening to the detector. Some of those things you expect, seismic activity to contribute to, and other ones you don't. So we cross-correlate all this data and we rule out all of the crazy possible sources of noise. And believe me, we have tons of them. This device is extremely sensitive and it is super hard to refine it and get it just right. And that's why it took us so long to actually make our announcements, because we wanted to cross all of our T's and dot all of our I's and really make sure that we were absolutely 100% confident that what we were seeing was from a gravitational wave. Although, sometimes we're just lucky. And we compare the data we get to the models we use to predict, and the match is just so good that it's hard to argue it's anything but gravitational waves. The next questions are there any plans for space-based gravitational wave observatories? And the answer is yes. The LISA mission, you've actually probably heard of it if you were a science enthusiast. They actually sent up the so-called LISA Pathfinder as a proof of concept a little while ago. LISA is a giant interferometer that takes all of that seismic noise out of the equation. It's 3 satellites that'll be arranged in a triangle, and it will work like an interferometer just like LIGO, Virgo, Geo, and Cagra do, except it'll be out in space. Now, because this detector is so much bigger, it's going to be sensitive to different types of gravitational waves. So instead of the stellar mass black holes and neutron stars that we're seeing, LISA might also be able to see things like white dwarfs. In effect, LIGO is going to be like, say, the gamma ray telescopes. They see the really high frequency stuff. Space-based missions like LISA will see an entirely different class of object. And so we're going to start building out a gravitational wave spectrum. That gravitational wave spectrum will now span a whole bunch of different phenomena and give us different types of information in the same way different wavelengths of light do. All the way from the high frequency stuff like LIGO down to really low frequency stuff with things like pulsar timing arrays and stuff like that. It's a really young field. Remember, this first detection, less than 5 years ago. So it's still really new, and there's a lot of exciting stuff coming over the next couple of decades. So if you've ever wondered what it might have been like to be an astronomer in the age of Galileo or Newton when they were discovering these things about the universe for the first time with telescopes, you don't have to imagine anymore. You're living it right now. Let's see. Next we got, what did we learn about the structure of neutron stars? The truth of the matter is with only one binary neutron star event, you don't learn a ton. A little bit of constraints on how hard and how stiff they are, because that relates to the gravitational waveform that they would produce, and when they crash into each other, the aftermath that you get from it. So we've learned a little, but not a lot. The real benefit is going to be when we don't have 1 or 2 detections of binary neutron stars, but when we have hundreds. Because then we'll have hundreds of different scenarios that we can test all of our models against. Those observations will allow us to rule out some models and reinforce others, allowing us to ever better understand what actually makes up these hugely dense and compact objects. Would it be possible to ride gravitational waves for high-speed space travel? Probably not. Unfortunately, gravitational waves are so weak and individually they carry so little energy that setting up like a gravitational sail is just too hard. Made even worse by that, whereas you can create a mirror for light where light will come in, bounce off, and you'll get a little transfer of momentum to move that thing forward. And gravitational waves, you can't do that either. Gravitational waves are so weakly interacting that they don't even get stopped by the Earth. In fact, LIGO and Virgo and Cagra, they can detect gravitational waves that happen from the other side of the Earth traveling straight through. So, unfortunately, gravitational waves of space travel, probably not likely. What would be needed to capture the original inflation gravitational wave? So this is related to the fact that, theoretically at the beginning of the universe, when the Big Bang happened, we have all of this stuff. There's this huge period of inflation where the universe gets really big really fast. Now, those primordial gravitational waves, actually, we're not going to be able to detect them with LIGO. Wrong frequency. They're far too removed from the area that we're sensitive to. But there are indirect ways that those could show up, including in very precise measurements of the cosmic microwave background. So that's actually a place where light is probably going to help us out quite a bit. And depending on the nature of the waves, if you go down into the parts of the spectrum where you see pulsar timing arrays live, you might be able to see something there as well. Next question is, what limits the size of the mergers that we can observe? Is it the mass of the objects, the length of the arms? Certainly, larger detectors would be sensitive to weaker signals, but importantly, what actually determines whether or not LIGO, Virgo, or something can detect what's happening is actually the frequency of the orbit. Detectors like LIGO and Virgo and Cagra are sensitive from about 10 hertz, so that's 10 cycles per second, up to a few hundred or a few thousand hertz. So this is thousands of cycles per second, with the sweet spot being right around a few hundred. Now, that relates to the frequency of the orbit. the frequency of the orbit is governed by, amongst other things, the masses of the object and how separated they are. And as a rule of thumb, to get really fast orbits, which means you have to have really high, fast orbits means high frequencies, your objects have to be very close together. And the only time objects can be close enough together to have orbits that fast is if those objects are very compact. Compact objects, like black holes and neutron stars, which I will remind you, can fit, say, in Missouri, or for a neutron star, Boston Harbor. Although, spoiler alert, you don't want either of those in either of those places. Oh, hello from the west of Ireland. Are gravitational waves made up of dark energy and matter? Well, certainly dark matter, if it was clumped up in the right way and it was moving in the right way, because it is matter, it interacts gravitationally, it could produce gravitational waves in the same way regular matter could. However, gravitational waves are not themselves made of dark matter, nor are they made of dark energy. Not in the way that maybe we're thinking. Instead, gravitational waves come about whenever something with mass or energy moves around in ways that are not symmetric. So if I have a nice sphere and that sphere is just getting larger and smaller, no gravitational waves. If that sphere is rotating like this, also no gravitational waves. But if I wave my hand like this, my hand is producing gravitational waves. And because they're so weakly interacting, they're actually making their way across the world over to you right now in the west of Ireland. They'll be there in a couple of milliseconds. Unfortunately, things like this, the gravitational waves are really weak. So, not much luck there. Dark energy, that's another interesting open question. And there is, in fact, a relationship between dark energy and what we see in general relativity. Now, that is actually going to come back to this equation that we have here. See this symbol, that weird triangle looking thing? You can interpret this as a possible source of the thing that we call dark energy. It doesn't give an explanation of what dark energy is so much as it's a way of measuring its manifestation. And it does appear in Einstein's field equations, but it's a much larger effect. It happens on cosmological scales, like over the size of the universe, not so much on the scale of gravitational waves. Another good question for a curious 8-year-old. Why are black holes called black holes? Oh, such a good question. Thank you for asking. The reason they're called black holes is because their gravity is so strong that if there was light trying to get away from this object, it would be pulled back in. And so you can see, although in this image, which by the way is from the movie Interstellar, fun fact, brief aside about Interstellar. Remember those folks who I mentioned won the Nobel Prize? This guy right here, Kip Thorne, played a big part in the science of that film. Anyway, the black holes that we're talking about here are, if I can find my slides again, are so massive that light can't escape. So any light that would be inside this area would get pulled back in. So although we can see light from stuff outside the black hole, any light from inside can't escape. And so it will never make it to us, and so the black hole appears black. We wouldn't be able to see it. But if we could, and maybe if we could actually look and see those black holes merging into each other, I'll play this video for you. It might look something like this. See, the crazy heavy mass, the gravity of these two black holes is so strong that it's bending all of the light around it. But if you look at the black holes themselves, they're not emitting any light because all of the light near them is getting pulled in. And so the light can't escape. The object appears black, and once those two black holes come together and finally merge and settle down into their final form, one large black hole, you would notice if we looked right at it, we wouldn't see anything. It'd be black, hence black hole. But if you're worried about black holes pulling things in, don't worry. One, they're not like vacuum cleaners. They only work by gravity. A black hole in that way is just as dangerous as our sun is. But we're orbiting our sun pretty easily. And guess what? We're actually orbiting a black hole too. There's a giant black hole at the center of our galaxy that really is huge, and we're orbiting it just fine. The other thing is that it's actually pretty hard to aim up right, and even if you were trying to fall into a black hole, it's pretty tough. More likely you'd whip around it or you'd fall into orbit around it. So don't worry, black holes are perfectly safe and really super interesting. Next question, the loss of 3 solar masses, was this predicted mathematically or observed? Well, we definitely expected some mass to be lost. But specifically, the 3 solar masses that we saw from this event, that was a measurement we made based on the gravitational wave signal that we saw. So this was, it is absolutely predicted that this would happen, but this precise number came from observation. Do gravitational waves have the ability to influence the Earth's magnetic field? Ish. I say gravitational waves could certainly interact with matter that's interacting with the magnetic field. And certainly you can store energy in magnetic fields, and so there would be some very weak coupling between gravity and magnetic fields. But broadly speaking, no. Gravitational waves are so weak that even if there was a measurable effect, it would be a very minute one. Another good question. If you used higher frequency light, could you get a better resolution for the detector? This is an interesting question. And yes, absolutely. The wavelength of the light that you use plays an important role in how you build and how sensitive the device is. I think the laser light that LIGO uses is 1064 nanometers. So I believe that puts it in the ballpark of infrared. I could be wrong. I am not the instrument guy. I do most of my stuff with data analysis, but those wavelengths are chosen for a bunch of competing reasons. One of the things is higher frequency light means the photons have more energy. More energy means that when they hit the mirror harder. That puts more heat into the mirror, which causes things to vibrate more, which actually makes things more noisy. On the same hand, if you have too little energy, you're not going to be able to get a good measurement, because you definitely get more sensitivity with more power in the beam, but you run into issues with noise sources. So it's a very careful balancing act, and scientists over the course of a couple of decades narrowed it down to the right type of laser for the specific type of setup that LIGO has. But of course, different detectors might use different lasers because their setups are slightly differently. Why do gravitational waves and electromagnetic waves have the same speed? That's a super interesting question, and actually I should challenge some of my GR students who are in the live stream right now to try to answer that for you. And it'd be a good way to, they're working on their second exam, take-home exam right now, so that would be a good question for them to answer. But I'll give you a partial answer at least. The speed of light, it turns out, is actually a very universal number. It is one of the few numbers that absolutely everyone everywhere in the universe will always agree on. And this is a little weird. What reason I say it's weird is if we come back to the scenario where we had Einstein and his cars moving around. Well, imagine I had this car here, and let's say it was speeding down the highway at almost the speed of light. Now, if it turned on its headlights, you would expect speed of light for the car plus the speed of light for the headlights. You would expect that to be twice the speed of light. Well, that's not how it works, actually. Speed of light, still the speed of light. In fact, one of Einstein's foundational principles of relativity was that the speed of light was a constant that all observers would agree on, no matter how they were looking at a problem. And it is precisely that weirdness that makes this complicated space-time. It's what allows that space-time, amongst other things, to bend and twist in ways that affect measurable outcomes. Another question about tabletop interferometers. Actually, I have a shout out to a student of mine who is working on his very own tabletop interferometer for demonstration purposes. Are they strong enough to measure gravitational waves? And just at this stage right now, probably not. The reason being is the only reason LIGO was able to get down to the sensitivities it needed was because its arms were so long. Not only that, but we had those Fabry-Perot cavities that caused the light to bounce back and forth so many times. It's just so big, and we needed that to get down to the sensitivities we needed. It's just we don't have the engineering precision yet to be able to do that on tabletop scale. But maybe someday. Since the Earth and Moon are gravitationally linked, would the Earth vibrate if the Moon were to be hit by a very large object? Interesting question. And the vibration wouldn't happen the way you're thinking of it, because, if I clap my hands over here, that sends a sound wave over here, which could interact with something and cause it to vibrate. That's when somebody's driving down the highway and they have their subwoofer turned up and you can feel the thumping in your car. That's because the vibrations are traveling through a medium, specifically air, in the form of sound. And that medium allows you to influence things at a distance because there's actually a physical thing that's transmitting the vibrations. There's nothing between the Earth and the Moon. It's a vacuum. There might be a few specks of gas particles out there, but there aren't very many. So there's no mechanism for traditional vibration to make it through. But your insight about gravity was a good one. If there was a big enough collision that disrupted the Moon's orbit, yeah, there would absolutely be a push and pull with Earth, and we would feel that effect. Though I will say that while the gravitational effect of the Moon is quite pronounced, strong enough to cause tides, for example, the Moon is actually quite a bit smaller than Earth. So the disruption wouldn't be quite as crazy as it could otherwise be. Are most of the scientists working at LIGO engineers and computer scientists, or are there also physicists? There's everyone! We have computer scientists who handle our online databases, things like that. We have engineers who build the devices. We have physicists that design the devices that the engineers put in. We have physicists who are working on the theory that allows us to make improvements. We have physicists like myself who take the data and run it through computer algorithms to figure out what's in there. Every scope of scientists, from engineers to physicists, even to chemists, work in LIGO. It's a huge collaboration. I shouldn't just say LIGO, also Virgo and Cagra. We have thousands of scientists from all different walks of life studying all sorts of different things that were all drawn to this incredible project for completely different reasons. Mine, for example, was when I was a kid. I used to drive back and forth from home with my dad because we worked about an hour away and he worked in the same town where his parents were. And he'd drive me up in the morning, drop me off with my grandparents, I'd get to visit, and then he'd drive me home after work. And I spent time on those long drives home. Here I was, a 6-year-old kid on an hour-long car drive. This was before I had a smartphone. And I'd look up at the sky and I'd say hey, Dad, what are those cool things up there? They're points of light. And he'd explain it to me. And it sparked a lifelong passion in space for me. And then I went to school. I found out gravitational waves for a thing. I got to tip my hat to my advisor, Gaurav Khanna, who got me on this path, and my later advisor, Alessandra Corsi, who really got me a project I could sink my teeth into. And a whole bunch of dominoes led me to the specific science I do now, which is gravitational waves and gamma ray bursts. Every single scientist in LIGO, Virgo, and Cagra has their own story, and most of them are way different. Shout out for those of you who are looking, go Google right now, Humans of LIGO. Just Humans of LIGO. They feature all sorts of scientists, and you'll learn all sorts of incredible things about the cool and different people that work for collaborations like this one. How do gravitational waves benefit humanity? I love this question because it's a question we always get. We do Ask Me Anythings on Reddit every now and then. I've participated in a number of those. Just look for R-Coin. And this is a question I love to field. Now, the first answer to that is one of the ways gravitational waves benefits society is just by letting us write better textbooks. This is another tool that's going to allow us to better understand the universe, and we're going to make better models, and then we're going to find new observations that break those models, and we're going to have to come up with new models, and we're pushing science forward. Better science means better science textbooks, meaning we're all more informed and we can all learn more about what's going on around us. But hey, let's face it, that's an academic's answer to it, right? Because I'm an educator, so I have a vested interest. Now, gravitational waves aren't probably going to be built into your cell phone anytime soon, but what they do is demand ultra precision engineering. And that means things like the optics, the mirrors that we make, The suspensions, the scientists at GEO helped pioneer this process of extruding silica gel to hang the giant 50-kilogram mirrors from suspensions instead of regular cables, because those regular cables, they were vibrating too much. And so they extruded glass to hang from these things. That had never been done on the scale that it had been seen before. Every new engineering marvel that goes into a device like this has ripple effects throughout the engineering community. And some of the technologies that you depend on every day for the rest of your life in the future could have some, credit to give to the engineering masterpieces that are happening in detectors like LIGO. How does LIGO know where gravitational waves come from? Ooh, that's another excellent question. And the short answer is, if you just have one instrument, you don't. So let's take a look up at the night sky here for a second. So here's the night sky. If I have LIGO, one of my L-shaped detectors, and I detect a signal, all I can say is that the signal either came from there or there. More specifically, I can just rule out that it didn't come from a very small part of the sky. That's because one of these detectors, not really good at localizing where the event happened. But if you get two detectors, well, now the gravitational wave signal that starts up here is going to take different amounts of time to get to your first detector and your second detector. You can use that time delay to triangulate. Yes, the same thing your cell phone does with GPS, to triangulate the location. And two detectors do pretty well. They can get you to the ballpark of 1,000 square degrees on the sky, which is enormous. For context, put up your thumb, that's about half a degree. So 2,000 times more area than that. So what you want is more detectors. When you take your two detectors and you turn that into three, say, for example, by adding Virgo into the mix, that triangulation narrows it down from 1,000 square degrees to a few hundred square degrees. Add another detector like LIGO India or CAGRA, you keep improving your ability to tell where that signal came from. The more detectors you have, the better you can localize. This isn't a question, it's a comment. It says LEGO needs to come out with a LIGO model. Sign me up. Some of you should go and submit that to the submission thing that LEGO does, and I will buy that. Can we use gravitational waves to detect wormholes? Well, the first thing there is that wormholes, which are actually a legitimate prediction of general relativity, they would need to be real. See, the math that goes into general relativity allows for a lot of crazy solutions, but some of them are restricted by the laws of physics in the universe around us. So, for example, warp drive from Star Trek, there's a version of that that's technically possible, but you'd need a negative energy density, and we don't know what that is. It probably doesn't exist. So it means that in practice, it's not likely that we'll ever be able to build warp drive. But I'm telling you, if you figure it out, you come talk to me, because I'm interested. Wormholes are another example where it's something that's technically allowed, but the details of the solution are weird, and we're not really sure what it would look like. And while you, I'm sure, can predict the types of gravitational wave emissions that you would get from, say, a wormhole forming, it's not likely to be something we will be able to detect if it's something that even exists. If we could create a black hole in the trajectory of the Andromeda Galaxy, could we stop it from colliding with the Milky Way in a few billion years? Ooh, not likely. The size of the black hole you would need to be able to affect the trajectories of Andromeda and the Milky Way is just too big. But sure, I'll say that if you can make an impossibly large black hole and you can somehow do it safely and get it out there to divert the orbital paths of the two things, then yeah, gravity works. You could conceivably imagine something like that. What exactly is the calibration that takes place when LIGO is turned off for downtime? Bunch of different things, actually. Some of it is actually going in and taking the mirrors and the devices and tuning them and twisting them and doing very high precision measurements. Some of it is installing new systems that make the detector more sensitive. Some of it is fixing things that have broken in non-essential systems. And some of it is just turning it on and making it vibrate and making sure what comes out the other end is what you expect. It's a huge process. It involves dozens of people for every single one of these institutions that does it. And it's a huge undertaking, and it takes a lot of effort. The big jumps in sensitivity, though, those usually come from new things being installed, physical upgrades being put into the system rather than small incremental tweaks. How does LIGO get emergency observation time on Arecibo, Fermi, etc.? So these are satellites and observatories around the world that react to triggers. And that's actually not us. We have partnerships with all of these observatories, and these observatories want to follow up on the events that we are producing or are measuring, because this is the first time any of this stuff's ever been done. And again, I want to emphasize, I've only been doing it for 5 years. So this is still really new, cutting-edge science. And so these other observatories, which amongst others are shown on this plot, they all employ many great scientists that have their own specialties. And the ones, for example, shown here, signed up with us to work together on really refining these measurements. So it is an opt-in. And the answer in general is, if you want target of opportunity time on a telescope, write a really compelling proposal to the operators of that telescope and convince them that your emergency time is worth it. Okay, what did you do when you first heard of GW 150914, and what did you think when you first heard the news? Okay, so a couple of stories that I'd like to share here in the few minutes of time that I have before I have to let you all go. The first is that I was a young grad student when I first joined LIGO. This was back in 2012, 2013. So this was before the detection. I was just getting involved, and I'd go around and I'd give talks. Definitely nothing like this one. It was just a meek little me with a very different hat, telling the people about the cool little baby science I was doing. And folks were really engaged. But there was always somebody who would put up their hands and say, okay, kiddo, what are you going to do when this doesn't pan out? What are you going to do when LIGO turns back on and you don't detect anything? There was, right up to the moment of detection, a lot of uncertainty. I think people generally believed that gravitational waves existed. Hulse and Taylor proved that. But whether or not they'd be detectable and we'd be able to do astronomy, people were on the fence about whether or not we were there yet. And so when 150914 came around and the event was so clear, that was a big boon to us. You know, I was in the collaboration doing active postdoc work at the time of this event, and I remember getting the notice on my phone and seeing it and being like, wow. And I talked to the other postdocs and other faculty who were in LIGO, and within a relatively short time, just look at this. We were pretty convinced this was real. But we knew it'd be a long way to proving it. So we were elated. But we realized there was a lot of hard work to do. So we put our heads down, we buckled down, we did a lot of really great science over the next few months. You might be aware that it wasn't announced until, I believe, February of the following year. That delay that's how long it took us to really convince ourselves, never mind the rest of the community, that this was real. In a couple of weeks before the announcement, I was sitting at lunch with some faculty advisors and some fellow postdocs and a couple of grad students. And I want to emphasize that the group that I was working in, we were great. We had kept our lips sealed. We weren't talking about it. And other secrets had slipped out that, oh, maybe LIGO had found something, and people were asking us, but nope, we were good little scientists. We kept our mouths shut. I was sitting at lunch one day, and I told an anecdote that I love telling, so I'm going to tell it to you now. If you've ever been on a plane or on a bus or on a train, you have that situation where you sit down in your seat and there's somebody next to you. And maybe some pleasantries are observed, and sometimes that person will turn to you and ask, so, what do you do for a living? And so, let me give you a hint. If you're like me, you're from the Northeast, and you're like, oh man, talking in public is weird, just turn to them and say, oh, I'm a physicist. Most of the time, not all the time, but most of the time they'll go, whoa. I never liked physics, or I was bad at math, so I'm going to not talk to you. And by contrast, if you want to say, hey, you want to talk to them, you just say, oh, hey, I'm an astronomer. Because like all of you, all 215 of you out there watching the stream right now, I mean, how awesome is that? 215 people. Astronomy is awesome, and that will get the conversation going, I guarantee it. Just be ready for people to ask you questions about astronomy. Now, I was telling that anecdote at lunch. This was a couple of weeks before the announcement. And one of the faculty mentors, a gentleman who I have the utmost respect and fondness for, just turned to me and said, "Rob, don't you have to have detected something in order to call yourself an astronomer?" And here I am, knowing we're about to announce our first ever detection, but not being able to talk about it. I just had to shrink down into my sandwich and not say anything. Suffice to say, though, champagne was had when it officially became internally official. We had a great time of it. Another question, is LIGO's funding impacted by the political administration? So certainly LIGO is NSF funded, so we are impacted by NSF funding. A lot of individual principal investigators have their own grants that help fund LIGO research, and there's a huge cadre of funding agencies that have been essential to LIGO. And of course, the public enthusiasm for science helps the ebb and flow of how these things get funded. So if you're interested in this, make sure you're loud about it. Say how cool this stuff is and how much you want to see funding continue. Because while we do have funding and while there can be dips related to events like worldwide pandemics, at least those things tend to be spread out over longer periods of time. Funding on yearly or every couple of years or every few year cycles. So hopefully we won't see an immediate impact, but certainly from the current pandemic, we've seen that our institutions have had to shut down just for the safety of our people. Okay, wow, I think I made it to the end of the questions. So thank you all again for coming. I really hope that you enjoyed yourself. I know that I did. This was great. This was fun. And thank you to the AAA for inviting me here. This was a wonderful opportunity. And despite the technical hiccups, I'm sure I know that I had a great time. I hope that you did too. So with that said, I'm going to go ahead and pull up my title slide here. I'm going to duck off the stream and I'm going to hand it back to our hosts. Just before I do so, I want to mention that interestingly, another prediction of Einstein's relativity was just published. Some incredible observations of the orbit of a star around the supermassive black hole at the center of our galaxy. This is an artist's rendering of the orbit of that star, and it turns out that that star precesses slightly, meaning its orbit doesn't stay exactly in the right place. Scientists were able to take very precise measurements and quantify how much of that was, and it was in almost perfect agreement with Einstein's general relativity. I mention that for two reasons. One, because it's a cool thing about GR that's happening right now. And two, I mention it because my GR students who are in the chat right now just got this lecture on Schwarzschild precession. And so, hey folks, this is it in action right here. The incredibly hard homework and exams I have you subject to, it's all for something. So thanks again, folks. I'm going to pop off and let Irene come back on and close things up. We will be back in just a few moments.
All right. Thank you, everyone. I would just huge, tremendous thanks to Rob. Obviously, anything the comments say it all. But it's been an absolute pleasure to be working with you. thank you so much for coming in here and helping me with a lot of the tech. You have a great setup. You've been.
Thank you, everyone. Huge,
Sorry, leave me
tremendous
just.
thanks to
Oh
Rob,
no!
obviously.
Oh no!
I think the comments say it all.
I just want to, yeah, thank you so much. So we really look forward to having Rob again in person and being able to take him out to dinner and drinks, the whole 9 yards. I want to thank everyone who tuned in here and put up with our just minor difficulties. Really, the way Rob pulled a lot of this together has been really, really tremendous. So thanks to all the students, all the AAA people, and everyone else who just tuned in. I just wanted to share two quick things that I think I have here for you. Yes, humans of LIGO. Not all humans, apparently. There's a coyote, okay. And yes, there's also, someone said this actually does exist. So here we have Lego LIGO in all of its glory. So again, big thanks to everyone for coming out. Sorry, David Croft couldn't make it back on, but really thanks to him. Everyone, thank you again, Rob. Have a wonderful, wonderful night, and we hope to see you in more of our live streaming events. Follow us, follow Rob, and stay safe out there. Good night, everyone.